So how do we calculate oxidation numbers, oxidation states? Well, there are certain rules you can follow. The first one I mentioned in a previous slide. If you have an atom on its own or interacting with other atoms of the same element, then the oxidation number is 0, because that atom in that compound, because it's attached to other atoms of the same type, has not gained or lost control of electrons with respect to how it would be if it were on its own. So when you have a compound like H2, when you have a compound of like O2, when you have phosphorus, for example, it typically reacts with phosphorus can be found with 4 atoms of phosphorus. All the metals, when they're on their own, those oxidation states, so those oxidation numbers are 0. And it doesn't mean that they don't have electrons. That's not what it means. What it means is that those atoms in those compounds are not controlling more or less electrons that they would be if they were on their own, because they're attached to they are either on their own. For example, if you have the gas helium, or they are attached to other atoms of the same element. Another rule: when you have an ion, as what we call a simple ion, typically a cation, the oxidation number is the charge of the ion. For example, the group 1 alkali metal ions like sodium, lithium, sodium, potassium, beryllium, and they all have an oxidation number of +1, because that's the charge of their ion. For example, sodium in the compound NaCl has an oxidation state of +1. You have the alkaline earth ions, the group 2, and those have an oxidation state of +2. Calcium, magnesium, barium, rhodium. We're talking about that sort of metals. You have, for example, aluminium, which is typically aluminium 3+, has an oxidation state of +3. So when you have a monatomic ion, and especially if you have a metal of the first and the second groups, then the oxidation number is equal to the charge of the ion. When you have unknown metals, you usually, although not always, have negative oxidation numbers, because in general, metals tend to donate electrons, so it's natural that they tend to go for positive oxidation numbers, they lose electrons, and non-metals tend to gain electrons. And they tend to have negative oxidation numbers. So that's not always the case, as you can see in some of the examples. For example, oxygen, typically, except in certain compounds where it's called a peroxide, they're called peroxides, and the typical example of a peroxide is hydrogen peroxide. Typically, the oxidation number of oxygen is -2. So typically, when you compare oxygen on its own and oxygen forming part of a compound, that oxygen in the compound will have gained access to 2 electrons. That is controlling 2 electrons that it will not control if it were on its own. Hydrogen has a very strong tendency to lose 1 electron. It's a behavior that it has. It's its most typical behavior. So typically, the oxidation number of hydrogen is +1. The only exception is when hydrogen is bound to atoms or elements that have even a stronger tendency than itself to lose electrons. And the typical example is the groups 1 and 2, alkalines and earth alkalis. So when you have what we call hydrates, and I'm talking about compounds like, for example, sodium hydride or calcium hydride, here the oxidation state of that hydrogen is -1, because it's attached to an atom, an element that it has even a stronger tendency in that hydrogen to lose control of 1 electron. So in a normal compound, for most compounds, the oxidation number of hydrogen is +1. And I'm thinking, for example, the compound hydrogen chloride, that oxidation number is +1, except when hydrogen is bound to metals, especially from the first and the second group, alkalis and earth alkaline metals, in which it's bound to atoms that having a stronger tendency than itself to lose control of one electron. And that then the hydrogen is forced to accept an electron and operates with an oxidation number of -2. Oxidation number of halogens, fluorine, chlorine, bromine, iodine, typically is -1, because typically they have a very strong tendency to gain one electron. The only exception is when they are combined with oxygen. For example, I've got here ClO4 minus. That's the fragment is called perchlorate. And in that sort of compounds, for example, you could have it as an acid, perchloric acid. That chlorine there has an oxidation state which is positive, and we can talk about what number in a while. But the moment, let's focus on that. So when halogens are in a typical compound, attached to anything except oxygen, they have an oxidation state of -1. When they are combined with oxygen, and they have quite a few compounds that they are combined with oxygen, with 1 atom, 2, 3, or 4 atoms of oxygen typically, then they have a positive oxidation number, and the number will change depending on the number of oxygen atoms they are attached to. A couple of other useful rules when we're looking about calculating oxidation numbers. And remember, the goal of calculating oxidation numbers is that we want to identify in an easy or relatively easy way if a reaction is redox or not. Because if it's spontaneous, it will give us electricity. So it's interesting for us to know if a reaction is going to be redox. So the sum of the oxidation numbers for a compound that is neutral will be 0. If you have the compound, I've got here the example of magnesium chloride, but I'm going to give you another example. Let's say the compound NaCl. So NaCl, we have 2 atoms that previous rules have told us what their oxidation numbers are going to be. Sodium typically has, because it's an alkaline metal ion, has a very strong tendency to lose 1 electron. So the oxidation state of sodium will be +1. And about chlorine, chlorine has a strong tendency, except when it's attached to oxygen, to gain 1 electron, gain control of 1 electron. So the oxidation state of the chlorine will be -1. And when they are in the compound NaCl, the electron that sodium is not controlling is being controlled by the chlorine. So in total, these numbers have to adapt to 0, because that compound NaCl is a neutral compound. What happens with the example I've got in the slide, magnesium chloride? Well, magnesium is an earth alkaline, so very strong tendency to lose control of 2 electrons. So the oxidation state of magnesium in that compound is 2+. It has lost control of 2 electrons. Chlorine in that compound is not attached to oxygen, which is the exception we have mentioned in a previous slide. So the oxidation state of chlorine in that compound is -1. Each of the chlorines have gained control of 1 electron, that they come both from the magnesium. So overall, if I add up the charges, the +2 from the magnesium, if I add up, no, they can be charges in this case, but it's more correct to say, if I add up to oxidation numbers, I've got the magnesium that has +2, and the chlorine that has -1, and I have 2 of them, and they add up to 0. So the oxidation number of chlorine is -1, and I have two of them. And that's an important distinction. The oxidation number is intrinsic to that element, that atom in that particular compound. And you can have many of them. You can have 2 chlorines, or you could have 27 chlorines. Each of them would still have the same oxidation number, -1. And that's a very interesting distinction that is worth that you keep in mind, because if not, you will find it very complicated to calculate oxidation numbers or to keep track of which oxidation numbers change or not. And sometimes we don't have a neutral compound, we have an ion. For example, the H3O plus, the hydrogen ion. Or we could have, for example, the sulfate anion, SO4 2-, or the nitrate anion. So sometimes we don't have a neutral compound, sometimes we have a fragment of a compound, a polyatomic ion. So the oxidation numbers do not add to 0, they add up to whichever charge that ion has. So, for example, if we look at the ion H3O plus, hydrogen in that compound is not attached to a metal from the group 1 or 2 specifically, so the oxidation state is going to be +1. You have 3 atoms of hydrogen in that ion, but each of them does have an oxidation state of +1. And you have the oxygen. The oxygen is not attached to a, well, it's not in a peroxide. Remember, the peroxide structure is this one, H2O2, and that would be a different oxidation number. That would be a -1 oxidation number. But in all the other compounds, the oxidation number of oxygen is -2, and you have one of them. So if I add up all those oxidation numbers, 1 times 3, because I have 3 hydrogens, and a -2 because I have 1 oxygen, that adds up to +1. And that adds up to the charge of the hydrogen ion, which is +1. So the oxidation numbers add up to 0 if you are looking at a compound, if it's neutral, or the charge of the ion if you are looking at the oxidation number of a polyatomic ion.